All right. So I hope the sorting assignment's going all right. Remember, it's due Wednesday, so you got a few more days. I'm sorry I wasn't in this weekend at all. I was actually working mostly on your lab for this week, this whole weekend. It takes longer than you'd think to make up a whole lab. You know, and you think, oh, it's just making up a lab. It just takes longer than you think. So I forgot to put this up at the end of class yesterday. You can take a little look at this if you want, and then of course you can just search for it online. Just search for XKCD sorting, and you will find this one. And it's pretty funny, I think. So that's that. Hopefully your sorts won't look like this. But let me know if you have any other questions. I will be around over the next couple days, and then Wednesday I'll plan on being around most of the day. So if you do have any other concerns on homework, what is it, homework 5, let me know. Homework 6 we're actually going to publish on Wednesday, so it's going to come kind of right back to back. Homework 6 is it's the hardest program of the year, although I'm actually going to show you something today that I think is going to make it significantly easier. Bruce told me, oh, that makes it trivial. You can't make it that easy for him. So I'm going to make it a little easier, and then hopefully nobody will complain. But I think it's still a very interesting problem. I'm just going to make it slightly easier than like lots of slogging through stuff that you've already kind of done before. I'll get to that on Wednesday when I actually introduce it. Any questions before we get going? Okay, I handed back homework 4. Hopefully you saw the grades for that. If you have questions, I've already gotten a couple emails where we screwed up grading. I'll fix those, and we'll go from there. All right, what are we doing today? Well, guess what? We are finally getting to this topic called hashing. And remember all the way back on day 1, which was like 3 snow days ago and many months ago, I showed you a hash table implementation of integer containers, and we saw that it was like super duper fast, right? Which is cool, and the reason it's super fast we'll get to today. Well, actually, yeah, we'll get to it mostly today. But we will actually start to see why many things use hashing as their underlying data structure. Okay, it's particularly important in computer science because it makes things pretty fast. Okay, so we'll get to that today. Before we do that, this thing that I'm going to make your life easier on the last homework assignment is the vector container. Now, I forget if we've actually used a vector container yet. We've used a queue and a stack container in one of the labs. It's a built-in container that does all of the underlying work for a dynamic array completely for you. Okay? And part of the reason I wanted to show you to show this to you was, number 1, because it's going to make your life easier on homework 6. But number 2, I actually was talking to someone a couple weeks ago who's in the class, and she asked me about another project she was working for in a different class. And she said, I'm writing this program in C++, and I'm not sure why it's not working, blah, blah, blah. And she said, oh, I'm using a dynamic array, which I thought, hey, that's great. But then I thought, so we teach dynamics arrays in this class, and you should know how to write them, and you should know all about them. But when there's one that actually is built in, that's like that runs perfectly, you should probably at least know how to use it, right? And if you're going to go write your own C++ programs, let's say you went to an internship or you went to another, to get a job, and your boss said, hey, you need to implement something, blah, 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 and you go and you make up your own dynamic array class and blah, blah, blah. Your boss is probably going to be like, why did you waste all that time doing that when there's a vector built in, right? That actually works perfectly right off the bat. So I don't want you to leave this class thinking that C++ makes you do all of these like low level stuff. There is some high level stuff in C++, which is part of the reason it's such an important and widely used language, because it has things like this. Okay, that aside, and I'm telling you all this because I'm feeling a little guilty about making this easier for you on the homework, but you'll see. We're going to talk about vectors and then 2D vectors, and then today's lab. Did you guys get the email last night I sent about today's lab? Have you started looking at the lab yet? It's hard to do because you've got this other assignment, whatever. Please read it over before class, okay? Before the lab, because you got at least, it's like 4.5 pages long, and it's kind of intense. But I want you to kind of have an underlying reason so that you can get some stuff done in lab. This is a pretty intense lab, as it turns out. This is what I spent all weekend writing, so Oh well. OK, we'll talk about that. We'll talk about today's lab, and then we'll do the hashing stuff. OK? All right. The final project. This is like spoiler alert, but the final project is on the game called Boggle. Anybody ever played the game called Boggle? OK, yeah, it's a pretty kind of a fun game. It's like really frustrating if you don't have a big vocabulary, like kind of like me. I have like tiny little vocabulary, and I'm terrible at it. But what Boggle is let me draw it up here for those who don't know. OK, Boggle is a little word game where you have a 4x4, or in some cases a 5x5 grid, like this, right? And in that grid, it's got a bunch of dice that have letters on them instead of numbers on them. And when you shake this thing all up, you end up with a 4x4 grid of like F, E, R, L, M, Q, U, which is one letter, which is kind of weird, but it's because Q is so weird. Let's see, A, another M, X, R, R, E, I don't know, P. It's hard to come up with letters just like that, right? Let's see, O and J and S, something like that. And it comes up like that. And then what you have to do in this game is there's a timer, and you have to come up with as many words as you can that are 3 letters more or longer, right? So that's what it is. So can somebody find a word on there that's 3 letters long or longer? What was it? Meal, M-E-A-L. Is that on there? Sorry, which one is it? M-E-A-L. By the way, I didn't tell you, you can go diagonally or left and right or up and down. OK? The assignment for the final assignment is, and this is kind of bugging me because I'm a little OCD. It's got to be an uppercase M. There we go. So this assignment is to actually be able to check results from somebody putting in their results for Boggle and solving the entire Boggle board for every word that happens in a particular dictionary. OK? So that's what we're going to have to do, and you're going to have to be able to do that. And there's like 3 different programs you've got to write, and it's still pretty intense. But notice that the nice thing about a Boggle board is that it is a square, and if you think about it, it leads itself very nicely to a 2-dimensional array, right? Because 4x4, 2-dimensional array, awesome. Well, does anybody actually want to write a dynamic 2D array? I'll give you my answer. Right? OK, we could do that. OK, and you could, I'm 100% certain that given enough time, you could create a 2-dimensional dynamic array. The problem with a 2-dimensional dynamic array is that you have to assign it dynamically, and then each individual, like you have to assign the rows dynamically, and then each row also has like a column associated with it dynamically as well, right? So those are just a little bit, and like a column position as well. And then you have a certain number of rows. And it's just not the easiest thing in the world to do. There's lots of news and deletes and checking and all this stuff. 2-dimensional vectors will actually solve that problem for you. OK? It does it so that you don't have to worry about calling new and delete and worrying about memory management. OK? And it's just everything is handled in the background. Now, there is a bit of a learning curve on how to actually use an array. It's not that hard, but I think you guys should know it going forward from this class. OK? You should know how to do that. The vector is a container, and it's just dynamic arrays. OK? And all the messy details are handled for you, and it's got lots of nice functions in it. It's got a size function for you, right? It's got you can find the last element or the first element without knowing how long it is. It's called the back of the array or the front of the array, and you can actually push elements onto the back or push them onto the front. Now you still have all the same issues with dynamic arrays. What's the asymptotic complexity of pushing onto the back of a dynamic array? Maybe you don't know this. Maybe I'll have to switch it back. It's constant, right? Because the back of the array is like the last element, and you know you can do it. What's the asymptotic complexity of pushing on the front of a dynamic array? Linear, thank you. All right, it's linear, and you've got to know those things even if you're using vectors. But again, the dirty little details are handled for you. So at this point, you're mature enough to get access to these, and we'll let you use them. Now, how do you use the vectors? Well, oh, this is small. Did not expect that to be so small. Hold on. what you do, and did I put it in here? There it is. I skipped a slide. Or I went backwards on a slide. Oh, no. Sorry, I didn't. We'll do it this way. There we go. OK, so here's how you use an actual vector. First you include vector, angle braces vector, right? And then you have the vector type, and then you put angle brackets. And you've seen this before for queues and stacks, right? And you put the type you're using in there, and then the name of the vector like that. OK? The nice thing about vectors is it allows you to, if your song or something is called this, underscore song, right? You can say a song for, and that gives you the fifth element in the song, just like arrays. It's actually an overloaded function that allows you to do that. So it feels very much like arrays in that sense. How do you actually push things onto the array, or actually like put things to the back? There's a function called push back, and then you actually can use the type that this is a string in this case, and you push it back onto that value. OK? So that's how it works. This is just this is actually a non-dynamic array here, and it's going to push all these guys onto this array that we've called. OK? Again, no need to worry about capacity. No need to worry about expanding. All of that's handled for you. Woohoo, right? Yeah, Zoe.
So you declare the vector in like vector the first line?
Yep. Declare the vector in the first line.
How does that relate to the second line?
Oh, this is a regular vector. This is a regular array. This was just so that this is just saying, hey, I'm gonna show you how to get all these values into the array. That's all, into the dynamic array. That's all. OK? Yeah. So that's all. So you declare it that way, and then you can push them back, called, to do that. OK? Once you do that, whoops, let's go over. There we go. Whoa, maybe not. Hang on. There we go. We'll go over here. Once you do that, come on, there we go. OK? What you can do is there's two different ways to print out, to like access the vector. The first way is using a regular old for loop like this. First get the size. Okay? By the way, one of the reasons we don't like to call the size inside the array, like size I equals 0, I is less than string list.size, is so you don't call that function again and again and again. Just wanted a little easier, like a little better way to do it. Size t is an integer type that you get back from the array, or from the size function. It's just an integer, for what it's worth, just an integer. And then you can like walk through the list one at a time, just like you would another array. So this should look very, very familiar. OK? It's just using the size to get the actual length and then walking through all the elements. This, on the other hand, the bottom one here, is a totally different way of doing it. This is what's called using an iterator, and that's something else you should probably know coming out of a C++ class. Right? If you go to an interview and you say, I know C++, and they go, oh, talk to me about iterators, and you go, what's an iterator? Right? You should probably know what that is. An iterator is a way to like walk through a list so that it's safe. In other words, you can go all the way to the end, and it won't actually go past the end. Watch how this works. There is a type called an iterator for all of these classes. You actually have to define it this way. You have to say vector, angle bracket, whatever your type is, colon, colon, iterator. And that's like the int I part, except it's now an iterator instead of an integer. And what you do is you then say, hey, start from the beginning of the list. Look at that. Go to the end of the list and just increment I. Right? And then what you do is to print it out, you are given a pointer to the actual element. OK? So to print it out, you print out asterisk I, and that will actually print it out for you. OK? Done.
Why is it plus I and not I?
Good question. Doesn't matter. Could have been I++. Right? Doesn't actually matter. It happens before the function gets done. Yep. I don't know why. I did it up there too. Plus I. It doesn't really matter. Yeah, sorry? Size t is an integer. It's just an integer. It's a particular size of integer. OK, here's the background real quickly on size t. When C was developed and when C++ were developed, when you say int, the computer says, I can give you a certain amount of memory, like a memory location to put that integer, and I get to decide how big it is. right? And so if you have a tiny little like computer, like an embedded computer or something, the int might only be 1 byte long, right? But if you come to a 64-bit computer, the int might be 64 bits long. And to make it more what we call portable, C++ said, get rid of all, like, don't get rid of ints and things, but make them so that we know that a size underscore t is exactly 64 bits long, for instance. So it's just a way of making it so that code works better across computers. That's all. But it's just an integer. You can think of it exactly like an integer. OK? All right. So that's kind of the intro to vectors. On today's lab, you'll practice using vectors in particular. OK? And as I mentioned, there are these things called, you can actually make 2D vectors. Here's how you make the 2D vector. You say vector, vector, because it's going to be a vector of vectors. You put a type in here, and then you have all these angle brackets. Notice this right here. This is kind of funny. That's actually a space right there, and you have to put that space. Because if you don't put that space, it looks like two angle brackets next to each other, and it thinks, oh, I'm like printing out or something. Right? So it's a syntax thing. Like it can't what's called the lexer or the parser for your actual language can't determine whether angle means what it means in this context. So when you get to if you ever take a compiler's class, you'll learn all about that. But anyway, what this is this is now a vector made up of vectors. Okay? Each vector now has a vector in it, just like your dynamic array would have an array inside the array. Okay. How do you access the elements? Well, what's nice is you can do it just like you would a two-dimensional array. You can say x, bracket y, and that will give you the xth over and the yth down, right? Or I should say, sorry, it's the other way around, the xth down and the yth over. Okay? The number x row and then y column over. That's what that will give you. Okay? And so that's how you do it. Now, you have to be a little careful with arrays with vectors, because you can't access a part of a vector that you haven't actually put into the vector first. Okay? For instance, let's start out with a vector. Okay? If I just declare a vector, it's going to have 0 elements in it. Okay? If I try to access the 0th element, does it exist yet? No, so I'll actually probably segfault or something like that. If I do my vector dot push back, push back parentheses, and then something like, I don't know, my string or whatever. If I do that, now my vec 0 does exist. Okay, so you can't try, it's not like a 2D array where you create it with a certain width and everything's filled in already but dead squirrels, and you create it with a certain height and everything's filled in dead squirrels. You have to do it yourself individually. So how do you do this? You first create a row, populate the row, put that row into the main two-dimensional vector, push it back into the main two-dimensional vector. Then you create the next row, push that back into the two-dimensional vector. Okay, so let's see, do I show you this? I think on the next page I might show you this. Yeah. Here's what you do. You create the vector, and then you create a first vector, which might be the row. You push a bunch of elements into that row, and then after all the elements are into that row, you push that row onto the original two-dimensional vector. Okay? Think of it like building up one block at a time. You have to build up a row, push that row into the vector. Build up another row, push that row into the vector. Build up another row, push that row into the vector. Does that make sense? It might not, but you'll practice it tonight. Okay? You'll practice it tonight. You don't automatically get the whole size. And part of the reason we don't get that is because you might not know the whole size. Right? For a 4x4 you might, but guess what? For the Boggle game, you have to be able to handle a Boggle board size of infinite width and infinite height. It's going to be square, yeah. It'll be square, but it'll be infinitely wide and then infinitely high, possibly. Well, it won't be infinite, but it'll be anything up. You have to be able to handle all the boards. Okay? Unfortunately, with Boggle, you'll quickly find out that enumerating all the solutions gets harder and harder the bigger you get. It's an n-squared type of problem. But that's it. OK, so you will see this in lab tonight. That's why I made this lab, so you can practice this. And tonight's lab is actually I think it's kind of fun. I had a fun time making it, and hopefully you'll have a fun time doing the coding for it. It's called Image Engine. And what it's going to do is, what you're going to do is you're going to be able to take an image and manipulate it much like Photoshop might do, right? You can take your image and flip it, or you can take your image and flip it upside down, or you can take your image and make it bigger or make it smaller, or do this other thing I call psychedelic, right? Should have waited till April 20th to do this lab. But it's psychedelic, right? Which is actually using the colors of this and actually shifting them left and right. Okay, I'll show you this. I'll show you what this means in a minute. Here's how. Has anybody ever looked at image formats before, like JPEGs or GIFs or GIFs or whatever you want to call them, right? Okay, a couple people have looked at them. Image formats are interesting. Most images you get are very highly compressed, right? They're very highly compressed. The image format we're using is not going to be compressed. Okay, the image format we're using is going to be basically, it's going to say, it's going to have this special number that says, hey, it's this type of image. Then it's going to have two numbers like 3 and 3 for 3 wide and 3 height, right? A width of 3 and a height of 3. And then it's going to have these triplets of colors, right? RGB, red, green, blue. If you remember your physics, right? Those are how we define the primary colors for light. Red, green, and blue. And what it'll say is it'll be like, oh, it'll also have what's the maximum color size that you can have. That's another thing. And then it says the 3 colors. So it might be like 0, 0, 0, I don't know, 255, 0, 0, and then 0, 20, 0, or 10, or something like that. And that'll be the first row. And the next row will be the next set of triplet numbers, et cetera. And that's the whole format. Okay? It's not compressed, which means the files get huge very easily, right? They get really, really big. You're going to take this format, and all you're going to have to deal with is the actual image data. We've taken care of all this for you. You're going to take the image data and you're going to manipulate it. Okay? You're going to manipulate it to do things like this. Okay? You're going to take the original image and you're going to scale it to 2 times. That's the one that I want you to be able to do by the end of this class, or by the end of lab. If you can get that function done, awesome. You're going to keep working on the other ones if you get that one done, but you're going to be able to hopefully get that one done. You're also going to be able to shrink it, right, which I didn't put on here. You're going to be able to shrink it down. You're also going to be able to do mirrored. Notice it's mirrored from there. You can also flip it over, straight over. We're not talking about rotation. You'll get to rotation in Comp 40. Okay? And psychedelic is just shifting the colors. So red becomes green, green becomes blue, blue becomes red. You're actually shifting all the colors over. Okay? And I'm sure you can think of lots of other cool things to do with this, right? You can do that. But let's talk about one of these. If I have an image, let's say I have an image that looks like this. It's actually got a little like frame around it. And then I have like that. If that's my image, if we want to double the size of it, okay, in both directions, think about how we might do that. Actually, talk to your neighbor about how we might double the size of this in both directions. If we have pixel, 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 and each pixel is 3 long, but don't worry about that. Just pretend it's pixel, 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 and pixel, 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 pixel. How do we actually double the size of that? Talk to your neighbor about that. Okay, does anybody have an idea? Who has an idea? Go ahead. you'll have each pixel take up 4 pixels. I will buy that, right? Because it's going to start with 1, and then it's going to end up being 2 that way and 2 this way. So it is going to take up 4 pixels. How do you actually do that, though? Think about it. Yeah, go ahead.
So what we said was that you go and start at the top left corner, and you go along until you find a different color of pixel, and so you've now got this distance.
You're way overthinking it. You're way overthinking it. All you need to do, I mean, think about it on a pixel by pixel basis. I like what you're thinking, but you're like going like way deeper than what we need. Good, very good idea, but too deep. Yeah.
Or you could double the index of the pixel and then copy it to the next one and then do the pixel double.
You're getting there. Yes. You had one comment? Oh, so sorry. Wait, I'll come back to you. Go ahead.
Maybe push each pixel twice and also push every row twice.
That's what I was looking for. Is that what you're going to say too? Yeah. That's basically what I was looking for. Because you're doubling it, you're going to do each pixel twice in both directions, which is kind of what everybody else was thinking about. But let's think about like the actual nuts and bolts of how we do it. For pixel 0, 0, what am I going to do for the first row? Pixel 0, 0 is going to be where in the new image? 0, 0. So I'll do it this way. I'll 0, 1, 2, 3, 4, 5, 6, 7. Everybody agrees that there's going to be that, right? 3, 4, 5, 6, 7 down there. OK, that one's going to be right here. OK, and then what are you going to do with that one again? Push it again right there. So this is a little for loop. For every pixel, we're going to duplicate it. Right? And you're just going to push it. You're going to basically look at this one and then push it onto the new row that you're created twice. Or if you're tripling the size, 3 times. Or if you're quadrupling the size, 4 times. It's a really easy image like doubling thing. OK, 0, 0. And then this one's going to do what? You're going to go for the next one in the row, same thing. The next one, same thing. And the next one, same thing. And notice we've now doubled the size of that row. Everybody get that idea? OK? So now, what are we going to do with this row? This is actually the easier part. We're going to make a whole row. Now we've got a whole row that we've just made, and that's our new dynamic array. And we're going to have to take that whole row and push it into the new image. How many times are we going to push it in? Twice. Don't copy it again. We're going to push it in twice. So now you're going to push that one in twice. So you're basically in the new image. You're going to double all these, push that row, and then push this row again. OK, oops. Yeah, that's it. So push this row again, and now we've got the same row here, twice. And it's twice big this way and twice big this way. And this pixel is the same as this one, and the same as this one, and the same as this one. OK? So it's like a bunch of for loops. That's all it is, a bunch of for loops, because you're going to do that. The next row, you're going to go to the next row, and you're going to create a new row. And the row is going to be double, double, skip, skip, double, double. And then you're going to repeat that row. Double, 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 skip, skip, double, double. And you see how now we're going to do the same thing. And then this one's going to be double, double, skip, skip, double, double. Oops, I went over. Double, double, double. Right? And we're going to do that again. Double, double, skip, skip, double, 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 double. And then the last row is going to be all the same. And you'll see, oops, I forgot to double it again. But down this way. But do you see how now we've got a twice as big square out of that? OK? That's how you're going to do it. Similar idea for shrinking by 2. Right? Instead of doubling each one, only every other pixel is going to get counted. Too bad for the odd pixels. Right? If you're shrinking an image, half the information's got to go away. Now, if you're doing fancy image manipulation and stuff, there's ways for making it so that the color, like it doesn't get all screwed up. We're going to be very straightforward on this. OK? Very straightforward. How about mirrored? How are we going to mirror the image left to right? Any ideas? Yeah? It's going to be square already, by the way.
Okay, so like 0, 0 becomes 0, max 3 minus 0.
Yeah, that's what's going to happen. So basically, you're saying put this one here. There's an easier way to do it if you're trying to push onto a new one. Yeah. Yeah, just go backwards through the row and push all those pieces, all those ones on. Go backwards through the row and push, 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 push. See how these things are not, they're not that hard. Like they're not, that's exactly what you have to do. But when you think about it in terms of looping, you have to think, wait a minute, what's the easiest way to get things into a new array? Go backwards. Question?
You showed us the iterator earlier. Can we go backwards?
You can. You have to do a reverse iterator, though. Right? It turns out it won't let you do the iterator straight up like that. You can do it, well, I think it might actually. You might be able to do the iterator backwards. You have to do a reverse iterator, but you can. You just look it up in the documentation. Okay? Flipped, same idea, right? The first, which row is going to get pushed in first? The bottom row. So go up in the rows, push the bottom on the top of the next one, the bottom on the top of the next one, and that will flip your whole image. Okay? These are not hard at all. They just take a little time to understand. Okay? You'll get to that. And then psychedelic's actually kind of cool. Psychedelic is if this was pixel 1, and this was pixel 2, and this was pixel 3, right? The red is going to get this one. This one's going to get this one. This one's going to get this one. So it's actually a pretty simple algorithm to do. You go through all the rows and all the columns, a double nested loop, all the rows and all the columns. And for every pixel, you just use a temporary one. You set the temporary one to this one. You set this one to this one. You set that to that one. You set the temporary. You get the temporary into this one. And that's it. So it's actually pretty simple to do. Okay? This stuff sounds hard, but once you do it. And by the way, you'll be able to check your answers, too, by opening up the images in the actual image program on the server computers. Okay? All right, questions about that? This image manipulation stuff is kind of fun. I think you'll enjoy it. No? All right. No, yes, you'll enjoy it. No, it's not. I meant no questions. All right, so that's that. Let us go into the next topic. Okay? As I said before, the next topic is hashing. Okay? This takes a little bit of setup. Okay? We have talked about keys and values a number of times, right? Priority queues are based on keys and values. Okay? Another way of thinking about keys and values are words, keys, and their definitions, values. Okay? So if you had an ox, and the definition would be bovine trained as a draft animal, right? There is a key and the value, which is there. Okay? The idea is we want to store these even more efficiently than all the other types of data structures that we've come up with so far. Okay? We want to store this nice and efficiently, and if we can do that, then we'll be able to have nice, fast-running programs. Okay? We've talked about all these things before. All these other different kinds of containers, lists, stacks and queues, trees, heaps, all that. They all have their own trade-offs, right? They all have some linear behavior or some logarithmic behavior, and log isn't bad, but they all have some trade-offs, right? We've never talked about one where every function is actually constant. Okay? We actually would love to find something where everything is constant. Okay? We want to be able to do find, insert, remove, all in constant time. Right? Because that's like the holy grail of computer science. Right? Being able to do all these functions in constant time. Okay? All the things we've talked about before are about storing items kind of in this nice orderly fashion. Right? If it's a linked list, there's one after the other. If it's an array, it's one after the other. If it's a tree, it's one after the other, but linked structure. Right? We're going to do this in a completely different manner. Okay? That's where this thing called hashing comes into play. Okay? And we're going to use these things called hash functions. And a function, just like in math class, is you take some number, you take basically some number, and you apply a bunch of mathematical things to it in a function, and you get another number out at the end. Okay? Those things are called hashes. They're also called hash codes. They're called hash values. Okay? And those are the things that we're going to actually produce with this function. So again, take a number, apply some function to it, get another number, and deal with that other number. Okay? That's what a hash function is. Okay. Hash functions have to have two features to them. They have to be deterministic, or hash codes must be deterministic. In other words, if I take a number and apply a hash function to it, it better come out the same way every single time. Okay? It better be the same value every single time. Now, that sounds trivial because mathematical functions will give you the same value every time, but it's a little more subtle than that. But we'll find out about that. They also should be fast. In other words, you want to have a function that's a mathematical function that does things relatively fast in most cases. We'll talk about the way when that isn't true sometime later, probably on Wednesday. Okay? And they should also be distributed. Now, who cares about this distributed, and what does this distributed actually mean? If I take a number and I put it into my hash function, I want that hash function to produce output numbers that are spread out among all the possible choices. Okay? I don't want them to all be grouped up in one little corner. If I put 0, 1, 2, 3, 4 into a hash function, I don't want all of the results to be bunched up in the one corner of my like resulting distribution. I want them to be nice and spread out. Okay? And I'm going to demonstrate that for you. Okay? Anybody notice these little things around the room? The little numbers? Some of you did. Some of you saw me putting them up earlier. What we're going to do is we're actually going to hash you guys. Okay? And by the end of this, you'll go, oh, I think I get what a hash function's good and bad at. Okay? All right. Everybody has a birthday, right? Hopefully you know your birthday. Hopefully you know what year you were born and what month and what day. Okay, because we're going to be hashing you, which is going to mean getting out of your seats. So put away your laptops and stuff for a few minutes. Okay, you're actually going to have to walk around the room here. And here's what we're going to do. Okay, we're going to do hashing and compressing based on your birthday. Okay, and if you want to make up your own birthday, that's fine. Like if you don't, like if you're like old or something like me and you want to like make up your own birthday, I don't really care. Just make sure that it's consistent. You can't change your birthday in the middle of this exercise. Okay, year, month, or day. Okay, here's what we're going to do. Okay, first things first. We're going to hash the decade of your birth year. Okay, so whatever year you were born in, whatever decade that was in other words, 70s, 80s, 90s, zeros, whatever, right? We're going to do that. So how do you figure that out? You take the year, you divide it by 10, and then you do the modulus of 10. Okay, so let's say you were born in 1932. Nobody's born in 1932? 1932 divided by 10 gives you 193, okay, because it's an integer division. Okay, and then modded by 10, well, 120, or what did I say, 193 mod 10 is what? 3, so you would go to the 3 bucket, which is back there. Okay, back there. And what you're going to do is, that's all you have to do. So whatever year, you're basically going to take it's going to be basically the tens digit, right? Okay, everybody got the idea? Okay, go to your buckets. This room's not big enough, is it? I know. If you want to choose your birthday, go right ahead. You can be born in the 30s if you want. All right, everybody else, you got your own birthday. Okay, so everybody is bunched up in the 9s except for people who chose their own birth year, right? Okay, why? Because all of you guys are in college. And most of you guys were born in the 90s, right? Okay, is anybody in the zeros? Nobody's in the zeros over here? Not quite. You have some youngsters here. You never know. I think there was a freshman here who's like 15 or something, right? But anyway, so here's the deal. Was the hash code deterministic? In other words, if I sat you all down again and said, go hash yourselves by the decade of your birth year, would you all go to the same place? Unless you made up a new birthday. But if you all go to the same place, right? Okay? All right. So it's definitely deterministic. Was it pretty fast? Was it hard to do this? Divide by 10 and mod by 10? No. I mean, that's two calculations, right? Okay. So that's that. There's a problem with this, though. You're all like over bunched over here. So is it distributed? No, it's not distributed. Okay, so that's the issue. You're all bunched over here because it's not a distributed hash function. Now we're going to hash the last digit of your birth year. Okay, so whatever your last digit was, go to that number now of your birth year. Those who made up the 30s, haha, you have to figure out which 30. Camille, what year were you born in? 97, yeah. So most of you guys are still bunched up on this side of the room. Was that deterministic, though? If I sat you down and said, go hash yourself by the last digit of your birth year, are you going to still go to the same place? Yeah, it is. It's definitely deterministic. Was it fast? Calculation was real easy. Year mod 10. Fast. Was it distributed? Well, it's a little more distributed, right? Most of you guys were born in like 96, 7, or 8, right? 4, 5, 6, is that what it is? 4, 5, 6? Okay. Well, sorry, 4, 5, 6. Couple 3s over here, a couple other like 1s. Were you actually born then, or was this a new year you made up? 91, there you go. So there's some other years. It's more distributed, but it's not particularly distributed. How about the last digit of your birth month? Last digit of your birth month, 1 through 12. Or I should say 1 through 12, but the last digit. All right, I see a little movement. Finally, people are ending up on this side of the room. There you go. Wait a minute, how are you in 0? Oh, 10, right? Yeah. I'm not thinking. I'm like, how are you in 0? Oh, it's the last digit. Okay, so guess what? Still, are we deterministic? Absolutely. Are we fast? That's an easy one, right? Month divided by or mod 10. Is it distributed? It's much more distributed. Look at the nice spread right now, right? Is it perfectly distributed? No. Why? Which numbers aren't going to be as highly represented? 1 and 2? I think those will be all right. How about 0, right? What's the only month you could be born in to get your last digit of your birth month in 0? October, right? The 10th. You can't do it otherwise, right? The only people over here are in October, so it's not perfectly distributed, right? And then some other ones are going to be more like which one were you saying was more? 1 and 2 are actually more, right? Because there are people born in 1 and 12, or 1 and 11, right? Or 2 and 12. So there's more over there, right? The rest are pretty well, but it's pretty well distributed. Okay? Can you think of an even better distributed one? How about the last digit of your birthday? Over there. Now, notice something, by the way. We changed the hash function and lots of people move. Almost everybody moves, right? And this causes a bit of an issue too, but we'll get to that a bit later. Okay. Just deterministic. Pretty much, right? You don't change the day you were born on too often. Fast. Yeah, very fast. Distributed. Look at the nice distribution we have now, right? Is it perfectly distributed? Not quite. Which numbers will probably have a few more? 1s might, 0s might. Because of which days? 30 and 31, right? Okay. So which ones? How about 9? Is that going to have just as many as 8, 7, 6, 5, 4? Probably not quite because of February 28th, right? So there'll be a couple more here. Anybody born on February 29th?
Oh, I was an hour away.
Oh, an hour away. I had like 4 people in my graduating high school class born on that day. So there you go. So do you see how hashing works now? You basically apply some function, which is this modulus function, and divides on here. And then you can spread things out just if you choose a good hash function. OK, grab a seat. While you're having a seat, I'll tell you my favorite birthday story. So when you're in the Navy, and if you go from if you travel west, in other words, when I was in the Navy, I started out going on ships from San Diego westward. All right, did I tell you this the first day of school? I might have. Going westward, if you keep going west, all right, what line do you eventually hit? The international date line, right? And if you keep going, you'll eventually hit the 0 line, which is way over or the 180, which is where Greenwich is, I guess, or 0 Greenwich is. I'm backwards. But anyway, you keep going west, you eventually hit that date. Well, in the Navy, what they do is, because you're going west every day, you're just continually sailing west. About every day and a half, you go through a whole other time zone, right? And it's kind of annoying to keep changing your clock. Although they do it. They change the clock pretty much every day or day and a half as you're going west. But they always do it at midnight. And they always do it at midnight no matter when you actually cross whatever the imaginary line is to do that hour change. They always do it at midnight. Well, when you get to the international date line, if you change the time at midnight, if you're going west, it might be Monday when you get to the line. And then at midnight, you change. And what day do you end up at? You end up at Wednesday. So you actually completely skip Tuesday. So you'll be sailing along, and it'll be like April 5th, and then you'll wake up in the morning, and it'll be April 7th. And if you're on a ship with 4,000 people, there's a fair number of people, proportionally, that had their birthday on the 6th. And the Navy took away their birthday. Right? So this actually happened to people on our ship, right? They're going along, they're like, oh, it's my birthday. No, you missed it. Right? And in some sense, that's a better story than any other story, right? I mean, if you're going to miss a birthday, it's because the Navy took it away from you. Is a pretty good story. But that's good. Going back the other way, if you're going east to west, so it's Monday, and you get to the international date line, and at midnight you change to the new day. What day does it become? Monday again, right? So you have 2 Mondays in a row. And if you happen to be on watch 2 Mondays in a row, the calendar is really wacky that week. It goes Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, right? They have to add an extra column on the calendar. And they had to take one away on the other one. So normally they just cross it out. But if you have to add more people, you have to add extra space. So it's definitely a little bit weird. But you know what we called that day? We called it Groundhog Day because of the movie. Right? It was just when I was first in the Navy. I'm going to date myself. When I was first in the Navy, that movie had kind of very recently come out. So before that, they didn't call it anything. But now they call it Groundhog Day. Yeah. Okay, it's my birthday story. Okay, but you get hashing. You get the idea of hashing now. We're going to start applying this. Okay. Let's step back a little and try to think about a good hashing function. Okay. Let's say that we want to take a two-letter words. And we're limiting ourselves to 2-letter words. Okay? And if we treat each character as a base 26 number, kind of like tries, okay? You've got 0 through 25 are the numbers you're going to do. Okay? To get that, if we assign every letter to a number, if we want to hash a particular word, 2-letter word, first we go to the first letter. So if we want to do ox, first we go to 14 and we multiply it by 26. Why? Because we're treating this as if it's a base 26 number. You'll see what happens in a minute. 26 times 14. Then you go to the second letter, x. X happens to be over here at 23. And you do 23 times 1. Remember how you do numbers in general. 47 is 4 times 10 plus 7 times 1. Why 10? Because it's a decimal number. 26 base 26 numbers are 14 times 26 plus 23 times 1, because it's 26 and 1. If we had 3-digit numbers, you'd have to do 26 times 26. But we're limiting ourselves to 2-letter words. You'll see why in a minute. Okay? At would be A is 0, 0 times 26, plus T, which is 19, times 1. It gives you 19. So this is a hash function. Is this a pretty fast hash function? Yeah, it's pretty fast. All you have to do is take the first letter, multiply by 26, and then add the second number. It's pretty fast. So that's good. Okay? And that's how we do it. Everybody kind of on board with how we're doing that? Okay? It is deterministic, and guess what? It's actually constant access if what we're going to do is map those letters into some array based on the hash. Notice the hash for ox was 387. The hash for at is 19. If we have an array where we're going to put the definition at that value, then you can get there in constant time. Let me walk you through it again. For ox, ox was 387. Put the definition of ox at position 387. One sec. If we put the definition at 387, how do you find out what the definition of ox is? You find 387 by doing the hash function. You go to 387, there's the definition. Constant behavior. Yes? Okay.
Would it be better, or is the point that in 387 that's the pointer to the definition of ox? That way you don't actually have to create an array that would store that.
Oh, good question. Yeah, you can do it a bunch of different ways. You can have these be individual two-letter objects, or you can have them pointers. It's completely up to you. Completely up to you. Yeah, Ben. That's a very good question. So Ben says, couldn't that result in multiple words being at the same index? The way we've defined this, just like, can 47 be the same as any other number? No, because the way we've defined this, every two-letter word has a unique hash function, or a unique hash value. Okay? Every two-letter word, because think about it, there's 26 times 26 different two-letter words, right? And you're putting them in their each individual position. It's just like saying 47 can be in the same place as some other number. It can't be. Okay, so it's a very good question. We will return to this in a little bit. Yeah, Zoe. How do I create, that's a good question. How do I create the number 47? 4 times 10 plus 7 times 1. How do I create the number 547? 5 times 100 plus 4 times 10 plus 7 times 1. It's a base 10 number. We're treating these little two-letter words as base 26 numbers. So how do I make ox? Ox is 14 times 26 because it's a base 26 number, right? So the 26 is like the tens column, except it's the 26th column, right? The 26th column, right? So we're going to do that, and then we're going to add x, which is at 23 times 1. It's exactly this. It's analogous to that. Okay, that's all there is to it. You can go back and look at that if you're getting a little more confused about that. Okay? All right. So now we can map these to our buckets, okay? 26 times 26 is how long this has to be, by the way. Okay? All right. We put the value into the array. The hashing takes constant time because it's just one value we're hashing. We don't have to worry about how many things are in this idea of a hash table, which we're creating. Okay? That array, we don't need to care about what's in there now. We're just gonna do the hash function and go right to that location. Okay? If the hash function is fast, we can also do it fast. So putting the value in is constant. Finding the value is constant. Deleting the value is constant because you find it and then delete it. All right? So all these operations are now constant behavior, which is the holy grail of hashing. Okay? Let's go back to this for a minute. Okay? Two-letter words and their definitions. Okay? We already said that 26 times 26, I'm enumerating it here for you, 676 different positions in our array. That will map every one of our two-letter words, which is brilliant. Okay? It's exactly what we want. Okay? All of our two-letter words. We actually call these, the array here, buckets. Kind of like we called the radix sort buckets. This is the bucket. In the array is where each one of those words goes. Okay? And if you don't believe me that there's only 676 two-letter words, Go try to like figure them out. You'll see that there's only 26 possible combinations for the first letter, 26 possible combinations for the second letter. 26 times 26 gives you all 676 words. Okay? All right. Anybody know Scheme or Lisp at all? We had a class a couple years ago where they actually had come into here knowing this. This is how you would define that in Lisp. Don't worry about that. Kind of a fun language. Here's how you might define it in C++. Okay? We're going to define the letters, and the words is the number of letters and letters, right? The hash code is just going to be the number of letters, 26, times the value of the letter. And we've seen this before, haven't we, in tries, where you subtract out a, and that gives you the value. A is 0, B is 1, etc. Multiply 26 by that, and then 1 times the second letter minus a. This is just what we were just talking about. It's just a little coding it up. That's your hash code. Okay? We're creating a word, and our dictionary here, right, is going to have a string of that many words. In other words, 26 times 26. To insert it in there, we just apply the hash code and then set it to the position that the hash code returns. Okay? And then to find it, we do the same thing. We apply the hash code and return the value at that position. Okay, so it's pretty straightforward. You guys can look at this later, about the details of this later, but this like wraps it up for you in this nice like fairly simple program. Yeah.
I don't know. This is like essentially useless code. Basically you're taking a word and you're using that to find this single word.
No, you're using it to find the definition. Right? So you're using it to find the definition, which is actually very important. Right? We don't store the words there. Later we'll find out that we actually do store the words and the definitions, but that's a different thing altogether. We'll get there. Okay? So we can store two-letter words. What if we wanted to store all English words? There's a word. There's 189,819 letters long. Those crazy chemists. It's a chemical name. It's disputed in the fact that, come on, that's not really a word. Right? It's like you're stringing a bunch of real chemical-like names together, and that's how chemists make long names. So that's, disputed. There are this is the longest published word. Somebody used a word, methionoglutamine, whatever, right? And I can't even fit it on here. 1,900 letters long, right? The longest word used by a major author is 183. I don't know what a major author means, but is that okay? There's the longest word in the dictionary. It's only 45 digits long. Supercalifragilisticexpialidocious is 34 letters long. Okay? And then a whole bunch of other ones here. Okay? Shakespeare used a word that was 27 letters long. Okay? And it also happens to be alternating constant and vowel. Constant vowel, constant value, etc. If we wanted to store all of these words, does our two-letter hash function work anymore? Now we're in trouble. Because if we're trying to do two-letter words, or if we're trying to do words, now instead of having 2 by 26 times 26, we would need to do 26 raised to the 189,819. 26 times 183 is more particles than there are in the entire universe. Okay, so you're not going to find an array that's even able to hold 26 to the 183. In fact, I bet 26 to the 45 is also bigger than all the particles in the entire universe. Okay, so we're not going to be able to use our method for this. Things break down a little bit. Okay, there's actually another place. This place here. This was a place in, anybody from New Zealand? I forget. Anybody been to New Zealand? A couple people in New Zealand? You ever been to this place? I spent a day driving out to this place. I saw the most amazing full rainbow that went right over the road. It was the most amazing thing I've ever seen in my life. Right? To get to this place. This is a place with the longest place name in the world. And it means the summit where Tamatea, the man with the big knees, whatever that means, the climber of mountains, the land swallower who traveled about, played his nose flute, whatever that means, right, to his loved one. That's what this all means. That's the name of the town. Drove all the way out there, took this picture, drove back, like 3 hours. But I got to see this place. It was in like the Let's Go book. So, All right, anyway, so we're in trouble if we're trying to store long, long words. Okay? Even just supercalifragilistic, 26 to the 34, way too many buckets. Never going to find that many buckets in an array. Just isn't going to work. Okay? English, though, only has 700,000 words or so. Right? It's a lot of words, but there's only 700,000 words or so. Can you imagine the empty space if you had 26 to the 34 spaces? Right? That's from here through like the end of the galaxy, each individual atom. If you were trying to store that and you only store 700,000 things, right? It would be completely empty, except so you'd never even be able to find a word, right? We should be able to compress these things a little bit better. Okay? Here's a better definition for a hash function. Okay? Any algorithm that maps data to a number that is deterministic and that maps to a fixed number of locations. In other words, it's not something that's huge. It's something that's fixed, and we can fix it at whatever we want. Okay? Ben, your point is going to come into play really soon. Okay? We need to conserve space, because we only have 700,000 words, but the words could be up to 26 to the 30, like 26 to the, or it could be up to, what do we say, 189,000 letters long or something, right? But what if we only want 700,000 words, we might want to use an array that's only like 800,000 elements wide, or maybe even 7,000, doesn't it, or 700,000. Okay? But we have to store arbitrary words, right? We have to store supercalifragilisticexpialidocious. So we've got an issue here. Okay? What we do is the following. Okay? And you guys, by the way, you did this for the birthday hashing thing. Okay? A good mapping is to do your hash code and then mod it by the number of buckets that you have. It's exactly what you guys did up here. Remember, every function happened to be the mod function, had the mod function in it? Okay? We only had 10 buckets here. I don't know if you noticed that, but there's only 10 buckets. And then a lot of you guys were sitting in various places. And Ben's point is very well taken, that you had to jumble up in buckets. The first one, you were all standing right here, and this was like one giant bucket. When we finally got to a nice distributed one, there were lots of places, but still there were multiple people per bucket, because there's more than 10 of you, number one. Okay? But here's how you limit it to the number of buckets. You just say, here's my hash function. I don't care what number it gives me. Mod it to the number of buckets, and it will fit in the number of buckets you have. Okay? Or at least it'll be placed in that bucket. Okay? Now we've got what we call a compressed hash function, or a compressed hash. Okay? Aha. Now, how do we deal with this? Well, or let's do a little bit more like theory about this. The number of keys is lowercase n, we're going to call it. The number of buckets is going to be uppercase n. So if we want to store 1,000 words, that's going to be lowercase n. If we have a bucket that's 5,000 buckets, that's going to be uppercase n. Okay? Generally, we want the number of buckets to be a little bit bigger than the number of keys, but not many. But they're much smaller than the number of possible keys. Okay? You'll see where this becomes interesting in a minute. So a hash table is kind of what we've been kind of talking about this whole time. A hash table maps a huge set of possible keys into n buckets because of this compression function. Okay? Do the hash code, mod it by n, and you get whatever that came out to be into one bucket, right? The month or the year that you were born, you had, well, basically 2,015 possibilities if we started at year 0, right? And you map those into 10 buckets by applying a division and a mod. Okay? All right. So let's talk about this a little bit more. Let's do another concrete example. Let's say that we can store integers. Here's what we're trying to store, all the integers. Our table size is only going to be 10 buckets, just like the one in the room here. Our hash code is going to be really simple. It's just going to be the number mod 10. Okay? So let's insert some numbers. What is 7 mod 10 going to be? 7. So where's it going to go? 7. Okay? 18 mod 10 is what? Where's it going to go? 8. Okay, 8 goes in 8. And yes, in this case, we're just doing the numbers, not some associated like value. But we're just going to hash the numbers themselves. Okay, 41, 1, and 34. Okay, how do we find them? How do you find which bucket 18 is in? Use the hash function, right? Here's what we could say. We could say, is 18 in our hash table yet? So we do the hash function, and we get 8, and we look in bucket 8, and we go, yep, 18's there. So it is there. So we found it. Right? If it wasn't there, if we were looking for 26, we would go to bucket 6 and say, oh, it's empty, so it's not in there yet. See how that works? That's how you find them. Can we perform a find max or a find min? How are you going to do it? How would you have to do it? You'd have to look through the entire array. There is no way to say, where's the minimum in this hash table? There's a problem. That's one of the issues with hash tables. You can't sort them like that. Okay? There's no sorting in these hash tables. Okay? What if we try to add 54? Ben can answer this question. Where's it supposed to go? Bucket 4. We have a little bit of a problem, right? Why do we have a problem? We have a problem because 34 and 54 are now trying to take up one bucket, and unless we figure out how to have two things go into one bucket, we're going to be in trouble. Now, with you guys, it was easy. You guys all stood here and said, we're all in the same bucket, right? Right? You can't quite do that with like an array, right? What solutions might we have? Yeah, Kayla. You could have a bucket of buckets. Sure. You could have a bucket of more arrays. Or what else could we have? A bucket of what? Like this actually starts to look like something. Maybe a linked list. You could have a little linked list here, right? 34, 54, blah, blah, blah. And you could do that. So you could make each bucket be a linked list. Okay? In fact, we have a word for this occurrence. It's called a collision. Okay? If you hash, when you're doing this mod thing, you're going to run into collisions. Okay? If you mod hash code 1, or if you do hash code 1 and hash code 2, actually I should put key 1 and key 2, not hash codes. If you do the hash function on key 1 and key 2 and they are the same, you've got a collision. Okay? We don't like collisions. Okay? One way for dealing with collisions is this. We just create a little chain. Okay? Chain is a linked list. And we're just going to basically have the linked list. For every bucket, it's going to have a linked list saying how many, or saying here's all the values that are in here. The problem is if you're only storing the keys, only storing the values, like the definitions, how do you know which one's your definition? No, you don't have to check all of them, because you do have to check. You have to check until you find it, but you also have to store your key as well as your value. So then you can go and check and say, is this my key? Yes, here's my value. Is this my key? Here's my value. Okay? Let me show you a picture here. This picture gets a little crazy, but this is pretty simple, right? Here's your table. It's going to point to some array. In the array, each element that has something in it is going to be a linked list. A novel and a book hashed to the position 0, and song and supercalifragilisticexpialidocious hashed to bucket 0. Swirl and spiral hashed to bucket 1. Nothing hashed to bucket 2, so that could be a null, or it could be an empty linked list, or whatever. This one hashes cat and mammal, etc. Okay, do you see how that works? It's just a linked list. So how do you find out if song is in the hash table? How would I do that? Yeah?
Go to the bucket and then go down the chain.
You'd go to the bucket. You'd hash the word song. And then you go to that position and you go, oh, it's a linked list. Is the first one song? No. Is the second one song? Yes. There's my definition. See how that works? What if we wanted to find ox, which we don't have in here, right? If we do ox, let's say ox maps to position 3. 0, 1, 2, 3. You'd go to the position 3 and you'd say, OK, is this one ox? No. Oh, there's none left. Ox is not in my table. See how that works? Now, there's a problem with this. What if you had a terrible distribution and everybody mapped to a link to a position 0? What kind of performance would we have? Linear performance. Right? We've got to go back to that if we have a terrible bucket selection. Okay? If we have a couple of bad things. What can we do with hash tables? We can do a few things. We can insert into them. We can find in a hash table, and we can remove from a hash table. Okay? This is a bunch of words on how you do that. Compute the keys, hash code, compress the function, and then insert it in that buckets list. Right? If we're doing a chaining situation. How do you find it? Hash the function, search the list. If you found it, return the entry. Otherwise, return null or some sentinel that says, nope, didn't find it. How do you remove it? Oh, this is tricky too. Well, it's not that tricky for this one. Hash the key, search the list, remove it from the list, and return the entry or return null, whichever you want. Okay? Hash functions. Insert, find, remove. As long as you have a good hash function and enough buckets, this will be constant behavior. The minute you have a bad hash function or too few buckets, you end up starting to get linear behavior, which is not what we want. Okay? If you try to insert two values with the same key, you've got a bunch of different approaches. Kind of like what we talked about with priority queues or heaps. Right? You can either replace the old value with the new one, or you can have both and have find arbitrarily remove one, or find one. That seems a little odd. You can also have a find all, which will remove all of them, or find all of the ones in there. Okay? But you decide what you want to do with that. Okay? You get to decide what you want to do with that. Okay. If you hash something based on the object's properties, if you change the object's properties, will you be able to find it again? You're going to be in trouble. Let's say that I hashed you based on your first name. No, how about this? How about I hashed you based on your last name? And people still sometimes when they let's say get married, might change their names, right? If I hashed you based on your last name and put you in the hash table based on your last name, and then a year from now you come back and now you've got a new last name, if I hash your new last name, am I going to be able to find you in that bucket there? Probably not, because it's probably going to hash to a totally different position. Okay? Probably not. So you have to be really careful with that. Okay? All right. What other things did I want to... the last thing I'm going to talk about today, the load factor. We'll start with this again next week, or on Wednesday. The load factor tells you whether or not you've got a good number of buckets and based on the number of keys that you're going to put into those buckets. Okay? If you have n keys and you have uppercase n buckets, the ratio of those two tells you how many or what the load factor of your table is. Okay? If we had 1,000 keys and 1,000 buckets, what would our load factor be? 1. That's not a very good load factor, because that means every bucket has to be unique in order for a perfect constant behavior for your hash table. Okay? So what we want is we want the load factor to be low. In other words, we want more buckets than the number of keys that we're going to store. And we might not know how many keys we're going to store, so we can actually expand this later, but we'll get to that. We also want the hash function to be good. And if there's no duplicate keys, then every operation is O1. If there are some duplicate keys, you might get an extra operation or two, but it's still going to be roughly order 1. Okay? That's the load factor. All right. That was a whirlwind introduction to hashing, but we will continue with hashing on Wednesday. Okay? See you guys in lab or on Wednesday.